We're sitting here in Cheyenne, Wyoming, in a famous laboratory on Bleecker Street. Oh, is it Beaker Street?
Bent Avenue.
Oh, Bent Avenue. Okay. Well, don't get all bent out of shape here, please. All right, and I'm staring down at a Dan Green who's going to talk about some magical technology. Go.
Okay, my magical technology. Basically, what Jim and I did over the last few years is try to find a better way to send power and data in the most efficient way over the smallest number of wires into a system that is self-protected, self-healing, and very survivable. We originally did this for aerospace, specifically micro-satellites. Since they can only weigh 500 kilograms, the amount of weight debt that you get from electronic bus structures fusing redundant wires for survivability is critical. So what we decided to do was make something that was lighter, easier, more reliable, and wouldn't require all of these structures that we just mentioned. I can start out by showing you, in fact, we have what we call a master control unit. I'm going to ask Jim if he'll put the power supply up here for me while I'm explaining it. The master control unit basically is the coordinator of the units themselves. It tells the other nodes or units what to do and when to do it. It keeps track of them. It lets you know how they're doing, what they're doing, and when they're doing it.
Now, what is Jim doing right now?
Jim's hooking us up to a 12-volt DC power supply.
And it's DC because of what?
We just made it DC because, number one, we had a DC power supply handy, but we can do DC or AC or a combination of the two within a given system.
And this is what's in your cars, 13.8 volts.
Okay, so this is really an automotive application.
Automotive application.
Could be. Okay.
But we've also designed it for spacecraft computers and other applications as well.
Great.
This particular version is set up for cars.
Okay.
For automobiles, for transportation systems.
Now what we did, in order to demonstrate the flexibility and capabilities of the system, is we made a few nodes, we call them, boxes. Each box performs a function. This one here, if you notice, has 5 LEDs at the top.
And so, is this supposed to represent something inside a vehicle, perhaps, or a function of some sort?
It could be a light, it could be a switch, it could be a thermostat.
Okay.
It could be anything that you have to turn on or turn off.
Okay.
And, speaking of turning on and off, this one is nothing but a switch. 2 switches, one switch that will run one appliance, one switch that will run another appliance, both coming out of the same box.
Okay.
We then have a voltmeter, because the amount of current that we can control and how precisely we can control that current is critical for any application that we're going to use that requires variable voltage, amperage, whatever it might happen to be. We have to be able to send that amount of power to that particular node without fail.
And this would be like your gas gauge. We have a sender unit and a receiver unit.
Which one is that now? The new.
This would be like your fuel gauge.
Okay, which gauge are you talking about right now?
This right here would be our receiving unit.
The voltmeter.
Yes. The voltmeter would be the receiving unit, for instance.
Okay.
Over here, if you notice, we have another voltmeter, but this is our sending unit. Now, under ideal circumstances, what this is measuring, from 0 to 15 volts DC, we should see exactly that same amount of current being delivered to this box over here as we adjust the feed. Also, you notice we have switches here. Now, these switches, if you remember, I said that these could represent anything that requires a switch to be turned on.
Mm-hmm.
These switches each control one of these LEDs.
I see. Okay.
We also, to show that we can handle high levels of interference and noise on the line, went out and got ourselves the nastiest old windshield wiper that we could find. This is the copper brush type. It creates a lot of EMI, and it shows the robustness of the system to be able to operate in a very noisy environment. Electronically noisy, that is. That I'll show you in a minute. Now,
There's one on the top there, Dan.
we also have, for instance, this could represent your headlight, or it could represent your tail light, or a turn signal. We then have these wires. If you notice, the wires themselves are nothing but twisted single strand wires. That's all it is, a twisted pair. They are polarized. In other words, you have, if you notice, a large and a small male insert, and that keeps you from making a mistake and turning this backwards and reversing the polarity.
Gotcha.
Now, what I'm going to do is going to separate out these wires a little bit first.
Can I start putting it together?
Not yet.
Yes,
Just a
ma'am.
minute. Just going to separate out the wires a little bit. Jim, if you would go ahead, please, and hook up the two wires that go to the power supply. That'll save us a little time.
Now, how are you hooking up these little black boxes we see on the table here now?
Just randomly. Doesn't
Now-
make any difference.
Wait,
what
so,
you
so
do.
wait, wait a minute. So you're telling me that it doesn't matter how these boxes are sequenced?
Makes absolutely no difference. In fact, we can go completely random in how we're going to do this. What we did one time for a demonstration is we took out a pair of dice. And whatever number came up, we gave each one of these things an arbitrary number, and that was the one we put next in series.
If you had a conventional wiring system in a common 2009 automobile, could you do that same thing with that vehicle or not?
Yes. It doesn't really matter in what order you hook up this system, because the system's intelligent.
Okay, but is a current automobile function the same way? Is it intelligent?
Not at all.
So in other words, with a current automobile, even a 2009, you'd have to hook up things in a particular sequence in order to have it function properly.
Not the sequence so much, but you must hook a certain thing, a certain light, a certain gauge, a certain motor to a certain switch at a certain location with a certain connection. It's a dedicated type of wiring.
So in other words, you don't have to worry about any of those specific connections
Correct.
in this system.
For instance, I could have one node sitting in the front of the car. I could have one node in the trunk of the car that could control your backup lights, your turn signals, your brake lights. I could have another node sitting in your dashboard that would control your radio, your heater, all your controls up there. I could have another node sitting in your back seat that would control your seat heaters, your speakers that are back there, etc. It really wouldn't matter because the nodes each have intelligence in them and they know what they're supposed to do and when they're supposed to do it. Now, so that we make this completely random,
On the side.
look,
I don't think it's coming up.
all right, John. Now, this is a twisted pair right now, but you can use, for instance, the chassis of a car as a chassis ground, and we could do this entire thing with a single wire instead of two. Since we don't have a chassis available, we're going to use a twisted pair. Now, what we're going to do is we're going to make a loop out of these things by hooking them up randomly. And since you're the photographer, I'm going to ask you to tell me which one you want next in line.
Point at one. So it does take the light.
The light. Okay, I'm going to hook the light up. And
Hook it to a voltmeter.
I'm going to hook it to the voltmeter. Do you want the voltmeter receiver or the voltmeter resender?
Right. Either one.
Okay, voltmeter receiver. I mean sender rather, here we go.
Okay, how about the 5 diode device?
Okay, the 5 diode device will be next. 1 second.
There's only 2 prongs there.
Okay.
And then you got a box with 2 switches in it, just hook that one up
box
next.
with 2 switches in it. You got it.
And what else you got left there?
What's left is the voltmeter receiver and the windshield wipers.
All right, windshield wipers.
Windshield wipers will be next after this.
And I'll let you figure out the last one. So I'm not smart enough to do that.
Through the process of elimination, I think we will have the voltmeter receiver as our last one. And then by hooking it back in to the main power, the master controller, we have now completed, if you'll notice, we have a loop.
Okay, so you've got every one of those devices is hooked together in a loop.
In a loop.
Okay.
Okay, now we'll turn on the power.
Okay, the top power has just gone on, and so
Now, let's start with the simple ones.
okay.
You notice these LEDs, we have 3 of them that are already on.
Hang on. Move.
Okay.
If you wait, hang on a second. Let me.
If you wish,
Okay, I see 3 LEDs.
can you cut it for just a minute, John?
What's that? Not a problem.
Yellow.
1, 2, 3.
Okay, starting off with our LEDs, which would represent something that needs to be turned on or off. Some sort of a switch, a light, a meter, whatever it might happen to be. The controls for these LEDs are actually here on this box next to it. If you notice, when I push, or when I hit a switch, we get a reaction. Another thing you will notice on this particular box is our voltmeter sending unit. Right
Okay.
now,
Just do me a favor. I've got both of those devices in the screen at the moment, and it would help if you would just try the switches so I can see what's happening to the LEDs while you're doing it.
certainly, I can be doing the switches,
Let me get over here. Now
Okay.
pull that up so you can see.
and
Actually, let's just take this and turn it around. That way.
So you've just turned the whole thing around and it's still functioning.
oh, it's
Right.
hot plug and play. Now, if you notice, Jim is hitting the buttons, we're getting the reactions.
Yep.
But now, if you also notice the position of our voltmeter needle, and if you notice this needle here, if you can see it clearly enough,
I can see clearly. Yes.
as Jim raises and lowers the voltage, we get the reaction here, even if I am pressing these buttons at the same time.
Now, let me push the button so that I'll get to it.
All right. Now, explain to me the following. I'm watching Dan hold the voltmeter, and I can see the needle switching back and forth because Jim is taking the other one, the one that Jim is holding, is also varying because he's got a variable knob on that to allow that to happen.
Correct.
Okay, so and we're seeing that voltage being reflected in the one that Dan's holding right now.
Absolutely.
Okay.
If you have something that you need at a certain voltage or at a certain regulation, a fan that you want to go slower or faster, you can control it this way.
Okay.
Another one is, notice we have 2 switches here. I just turned on the light.
Right.
We also have a switch that will go to our windshield wiper. We have slow speed and we have fast speed.
Okay.
And while this is all happening, if you can see, we are still getting precise control on
Okay.
our voltmeter.
All right, hang on. Let me come in on that now so I can get a
Take your
close-up.
time.
Okay, I see. So I'm seeing variable voltage at the one that Dan's holding, and then I'll go to the one that Jim has here, and we'll see that he is the one who's actually controlling the horizontal and the vertical. Right.
All right. Now, let's say for some reason you have an accident. A jack handle falls out of your trunk and it hits one of these wires. So let's just take this one.
Oh, so in essence, we've just lost one of the devices out of the system because of a lost connection.
No, we just lost a connection. We did not lose a device.
Well,
If you
well-
notice, the devices on both sides of that break continue to operate as if there was no brake.
So even though there's only one Y going, it's essentially like a brake in that system,
Correct.
it's still functioning.
It's now bi-directional. It is keeping everything running even though we have lost one connection.
One connection.
Now, what we can also do, this is what would be an open. Opens happen whenever you have a wire break on you or fall off. But you can also have what's called a short.
Right.
We went out and built a very simple short machine. And as you can see, we took the red wire and we soldered it to one end of a copper arm. We took the black wire, we soldered it to the other end of a copper arm. What happens when this is closed, as it is now, you have created a short.
Big time.
Because the red wire and the black wire are now sharing a common conduit.
I got you.
If we open up, we now no longer have a short. So let's say in operation, I'm going to put it right back in the same location. And let's say in operation, for some reason, you develop a short. As soon as I get this in together. Okay, now,
So it's functioning normally right now.
yeah, it's functioning normally right now. Everything's working the way it should. Take a look at the voltmeter again.
Hold on, let me just get in on it.
It's triple 90.
Oh, sorry, that light.
You got to hold it at more of an angle for me. That's better.
See what
Okay,
I
I can see the voltmeter still on
Okay,
there.
and if you notice, we also still have all of our LEDs and like this working. Okay, now, I'm going to put a short on the system.
Now, if you did that in a normal system that was connected all around like that, what would happen?
You just
Everything,
blew all your fuses.
everything would stop.
Or you would burn up your harness.
Okay.
But if you notice, we still have the voltmeter responding exactly the same way as it did before, and we still have all of our switches, lights, and everything else working the same way. If we decide to go in and fix the short, everything keeps right on working the same.
Now-
Again, hot plug and play.
Okay, now how is it possible that with that short in the system it keeps working? Because of what?
Because what it's done is it has detected a short between this node and this node and treated it rather like when we had an open. It realizes that current and information cannot flow between these two, and so it has terminated power and communications between them and gone bidirectionally.
So it's gone around them essentially and still allowed them to stay in the loop.
Self-healing. It can also, you could, depending upon how you wanted to use the system, it will even tell the master controller, we have it designed in such a way, it would even tell you, you've got a short right there. You've got an open right over here. You have a unit that's not operating the way it should. All these things would be available to the driver, the operator, whoever. I'm sorry, that light. Would be available to the driver, the operator, as a diagnostic tool. He would know if something was going wrong.
Just for curiosity, just while I'm standing here, just switch some of the devices around as far as how they're hooked in to
Certainly.
show that they continue to work or...
Put that one there, we'll put this one.
I'll put the light over here.